the next thing we're going to talk about is the P series. Now, we're going to jump right off of this harmonic series. So we're going to prove, well, we're not really going to prove this diverges, right? Even though this goes to 0, that's exactly why it does not automatically mean that this converges, because this particular one with a harmonic diverges. Now it looks like this. So here's theorem 10.10, harmonic series. So, okay, so here's the moral of the story. If I'm looking at this, oopsie daisy, I'm going to look at the family of P series. So P series here means I am looking at where I have my function is equal to 1 over x to the P. So what I really want to look at here in this P series is, what is this value of P? So I have, it doesn't have to be 1. It could be any number up here, any just integer, right? Well, any positive number, because if it's negative, that's alternating series, that makes a difference. So any positive number up here, just a number by itself, no variable. And then I have my variable to some exponent. And the P series focuses on this exponent. All right. Now, if you want to see the proof of this, you can email me and we can look at that. You can also look at the proof. I'm going to write it over here to the side. The proof is found in section 8.9, example 2. So you can look in your book at example in section 8.9 at example 2, and it gives you the proof because you use improper integrals in order to come up with this proof. And I would be happy to go through all of that with you, but it's not relevant to knowing the P series. I do the proof, like if we were sitting in class, I'd probably go through it just because I think it's nice for you to look at proofs sometimes, but half the time it confuses students. And so because we're already doing this virtual, I don't want to do anything that has the potential to confuse you, right? In class, we do a lot of questions asking back and forth whenever I go through this. So I'm just taking it out. I'm taking the proof out. You can find it there. You can email me. We can meet virtually to go through the proof. If that's important to you, we could do all of that. But I don't want to add anything additional to your plate because honestly, the proof doesn't matter. The result is what matters in what we actually use. All right. Okay. So if I'm focusing on this P here in this family of P series that we have, then what I'm actually saying, and this is theorem 10.12, that is in there, convergence of the P series. Oops. Convergence of the P series. And this is what it is. If I have a P series where I have this series, they're all infinite, of 1 over k to the P, it converges for P greater than 1 and diverges for P less than or equal to 1. If P equals 1, it is also called the harmonic series and diverges. As we see right here, if it's or equal to 1, and it's called harmonic series. So if you have the P series, then you literally just look at it, right? You look at whatever P is. If you just have a number over the variable to some, P is some number. If that value is greater than 1, automatic converges. There is no work to show. There is nothing you do. That's why you have to make that statement. You just say, therefore, converges by the P series. Look at this series up here. If I were to look at this example 1C, the divergence test is inconclusive. I would literally look at this and I would say, therefore, if I'm looking at the P series, the series, diverges by the harmonic series. Because P here is equal to 1. That's it. There's no other work to show. You don't have to do any of this. You just look at this and know that P is equal to 1 because my exponent is 1, diverges by the harmonic series, and that is where this comes into play. All right? You just literally look at that and come up with it. For instance, if you have here, example 1, which one is it? Oh, I turned my page here. Hang on. We just did C, so here's D. Example 1D, I have this series, K is going from 1 to infinity of 1 over K squared. Look at that right now. And what do you see? P is equal to 2. If I have 2, what is the relationship between 2 and 1? It's greater than 1. So looking back at my P series, if I have P that's greater than 1, what do you know? It converges. So literally we're writing, therefore, my series from 1 to infinity of 1 over K squared converges by the P series. That's literally all you have to write. Because I can look at this and say, oh, okay, my limit goes to 0, so I know the divergence test is out. But if I have that, then I can use my P series here, and then it helps me out. It's straight up exactly what it looks like is going down right there. All right, look at these. Let's skip over here to example 3 real quick. If I have K going from 1 to infinity of K to the negative 3. Oh my, what's another way of writing K to the negative 3? 1 over K cubed, you got it. So now what does that tell you? P is equal to 3, which is greater than 1, so my series diverges. What did I just say, diverges? That's not what I meant. Converges. Because it's greater than 1, right? I think I said the wrong word. Sorry about that. The series converges by the P series. Good. All right. Okay. Literally, the P series is absolutely outstandingly awesome because you can just look at it and come up with what's going on. That's what makes it super cool. All right. Let's do another one. Here's example 3B. K is going from 1 to infinity of 1 over the 4th root of K cubed. What's another way to write that? Yeah, how can you turn that radical into an exponent? Yep, 1 over K to the 3/4. And what do you know about 3/4? It's less than 1, meaning diverges by the P series. Nailed it. Therefore, the series diverges by the P series test. Oops. And literally that's it. Some of these tests are going to take more work to do them. Some of them do not. Like the P series, it's always nice when you can see that, bam, you come right to that answer, and that's super awesome. Now, was it 10.3 that we just covered not that long ago? Example 3C. We're going to use some of that convergence information over there. Now, remember whenever we were looking at this, we said that you can move one way or the other and it's still equivalent. Here's where that's coming into play. Here, I'm going to swing it back over to 10.3 because I've got it right here. That's awesome. Our rules, is right here. So if a positive integer here and I move this around, then it still converges or diverges, the same concept. Here's where that comes into play right here. So if I have this k minus 1, I can change this. If I'm going to put my very first value in here, it starts at 4. If I put a 4 in here, 4 minus 1 is 3, right? I can adjust k going from 3 to infinity of 1 over k squared. Do you see what just happened? If I were to plug that into these values, then I would have, if I'm going to write these out, I would have 1 over 3 squared plus, and then I would plug in a 5, right? If I plugged in a 5 right here, 5 minus 1 is 1 over 4 squared plus 1 over 5 squared, so on and so forth. If I'm looking at this one, we have 1 over 3 squared plus 1 over 4 squared plus 1 over 5 squared. Do you see how it's the same? Okay, when you adjust your starting point, because you have an easy little positive and negative, you have a constant in the numerator, an easy little plus or minus, you can adjust your starting point, and then that makes it easier. Now I'm looking at my series, and it's straight up P series, right? Yep. So now P is equal to 2, which is greater than 1, converges. Therefore, my series here, going from 3 to infinity of 1 over k squared, converges by the p-series test. Do you see what happened? Okay, so the deal with the p-series is you can literally just look at it.